On June 15, 2026, a U.S. Air Force B-52H Stratofortress suddenly crashed and burst into flames shortly after taking off from Edwards Air Force Base in California's Mojave Desert. All 8 people aboard were killed, including U.S. Air Force personnel, government civilian employees, and 2 Boeing employees. This was the deadliest B-52 accident since 1982. It was also the first B-52 destroyed in exactly 10 years since the fire at Guam in 2016. The aircraft involved was reportedly tail number 60-0061, a flying testbed supporting the integration of a new AESA radar for the B-52. So, what caused an 8-engine strategic bomber to lose control only minutes after leaving the runway? At 11:10 a.m., the B-52H began accelerating along the runway at Edwards. Because the test flight had only just begun, the aircraft was still carrying a very large amount of fuel. The B-52H has a maximum fuel capacity of 312,197 pounds, or approximately 141,610 kilograms. The aircraft also carried equipment for the new radar program, along with a mixed crew of 8. That was 3 more than the standard 5-person operating crew of a B-52H. Once it reached takeoff speed, the bomber raised its nose and lifted off the runway. Its landing gear began retracting as the aircraft continued climbing above the Mojave Desert. According to the tracking data cited in the report, the B-52 initially flew northeast. It then gradually turned north. During the first few minutes, the flight showed no clear sign of anything unusual. The aircraft continued climbing, but it had not yet traveled far from Edwards. That was important. The B-52 was still at low altitude and had not gained much room to deal with a serious emergency. If a problem appeared at this stage, the crew would have very little time to identify its cause and correct it. Only a few minutes later, the flight path suddenly changed. The B-52 made a sharp turn toward the northwest. Almost immediately, it began losing altitude at more than 5,000 feet per minute, or approximately 1,524 meters per minute. This did not resemble a controlled return to the base. The sharp turn and high descent rate indicated that the crew was facing a serious problem with the aircraft's controllability. At that altitude, they had only seconds to react. The B-52 is one of the largest military aircraft in the U.S. Air Force. When an aircraft of this size begins banking or lowering its nose at low altitude, the time available for recovery quickly disappears. At around 11:20 a.m., the B-52 struck the ground inside Edwards Air Force Base. The force of the impact, combined with the fuel aboard the aircraft, caused an intense fire. A fireball erupted in the desert and quickly developed into a column of black smoke rising hundreds of meters into the air. The smoke column could be seen from several miles away. Only about 10 minutes had passed since the aircraft began its takeoff. When emergency crews reached the area, nearly the entire shape of the B-52 had disappeared. The crash site was a scorched section of desert roughly the size of a football field. Fires continued to burn among wreckage scattered around the impact area. From the air, almost no large section of the aircraft could be identified. The scale of the destruction indicated that the crash had left almost no possibility of survival. At 12:48 p.m., Edwards officially suspended flight operations. Aircraft preparing to land were diverted elsewhere. Access routes to the crash site were sealed off. The base also stopped issuing non-commercial visitor passes. All available resources were now focused on the emergency response and the recovery of evidence. At 4:15 p.m., Colonel James Hayes, Vice Commander of the 412th Test Wing, held a press conference about the crash.
Today, Edwards Air Force Base experienced a horrible tragedy, and we lost 8 great Americans. This crash is deemed to be unsurvivable, and right now our thoughts and prayers are with the families of those that lost their loved ones.
From that point, attention shifted to what had caused the B-52 to lose control. Determining the cause could take up to 6 months, but according to Jeff Guzzetti, a former FAA and NTSB accident investigator, the speed at which the B-52 descended shortly after takeoff suggested that the aircraft had suffered a serious controllability problem. If we freeze the B-52 at the moment it began to bank, there are 3 areas that investigators would need to examine first: the wings and tail, the 8 engines beneath the wings, and the test equipment installed inside the nose. The first area is the mechanical flight control system. The B-52 uses cable linkages and mechanical components to transmit the pilot's inputs to the flaps and the control surfaces in the tail. When the pilot pulls back to raise the nose, these surfaces must move in the correct direction and to the correct angle. But if a cable or control surface had been installed or adjusted incorrectly during maintenance, the aircraft could respond differently from the pilot's command. This condition is often described as being rigged wrong. The 60-0061 had just left the runway. The pilot pulled back to continue raising the nose, but a control surface in the tail either failed to move or moved to the wrong angle. The B-52's nose continued to drop, or if the control surfaces on each side responded differently, one wing began to fall, pulling the aircraft into an increasingly steep bank. The pilot continued making corrections, but the aircraft still failed to respond properly. Because it was still too low, the ground approached before the crew could bring the B-52 back under control. If the flight controls were working normally, the next area to examine would be beneath the wings. The B-52H uses 8 Pratt & Whitney TF-33 engines arranged in 4 pairs. The failure of a single engine would normally not be enough to cause the aircraft to crash immediately, but if several engines on the same side lost thrust, the 2 sides of the aircraft would no longer be producing balanced power. The engines on the right suddenly lost power, while those on the left continued pushing the aircraft forward. This imbalance pulled the B-52's nose toward the side with the failed engines. The aircraft began rotating off course, a movement known as yaw. That movement then produced a roll, causing one wing to drop as the bank angle increased rapidly. The crew tried to use the control surfaces in the tail to keep the aircraft straight, but because the B-52 had only just taken off, its speed was still low, and the airflow over the tail might not have been strong enough to produce the corrective force required. The aircraft continued banking, lowered its nose, and lost altitude. Before the crew could recover, the ground was already too close. A similar multiple engine incident occurred at Andersen Air Force Base in Guam in 2016. A B-52H was accelerating along the runway when cockpit indications showed that 4 engines under the right wing had lost thrust. The crew immediately aborted the takeoff at high speed. However, the aircraft could not stop before reaching the end of the runway. It overran the runway by about 300 feet and caught fire. All 7 people aboard escaped, but the B-52 was completely destroyed. The key difference was the position of the 2 aircraft. At Guam, the B-52 was still on the ground. The crew could abort the takeoff, wait for the aircraft to stop, and then evacuate. At Edwards, the 60-0061 had already left the runway, if several engines on the same side had lost thrust. The crew no longer had a runway on which to stop. The aircraft had also not gained enough altitude to recover before the ground came too close. The final area is the AN/APQ-188A ESA radar system inside the nose of the 60-0061, but this was more than a standalone radar. It also used 2 DSSP processors, 2 8x20-inch touchscreen displays, a liquid cooling system, and a heating system powered by engine bleed air. All of these components were connected to the B-52's electrical network and computer systems. An electrical overload could have caused several systems to lose power at the same time. Leaking coolant could also have caused a short circuit inside the electronics bay. A software integration failure could have caused the displays to flicker or shut down completely. Multiple warnings would then have appeared in the cockpit at the same time. The crew would have needed to keep the B-52 climbing while also identifying which system was failing. If the problem spread to the computers, displays, or other critical control tools, they could have lost vital information while the aircraft was still very close to the ground. A delay of only a few seconds could have caused the B-52 to drift off course, bank, and begin losing altitude. By the time the crew understood the severity of the problem, the aircraft might no longer have had enough room to recover. There is currently no evidence confirming that the new radar caused the accident. However, because it was the largest technical modification aboard the 60-0061, investigators will certainly examine the radar, electrical network, cooling system, and integrated software. A failure in the flight control system, multiple engines losing thrust, or a malfunction involving the new radar equipment. For now, all 3 remain possibilities under consideration, but the crash killed 8 people. It destroyed a bomber that cannot be replaced by a newly produced aircraft and disrupted an important U.S. Air Force radar test program. The real answer still lies within the scorched desert at Edwards. And if you want to keep exploring secret operations and little-known military stories, stay with us in the next videos.